All right, we're going to move on to 2.3. I talked about, we were at 2.1 where we were graphing. We graphed x squared, x cubed, absolute value of x, the square root of x. We can even graph the cube root of x. Well, we first looked at all these three as expressions. Then we rewrote them as equations. That's how we saw them last time. All of these, we had y equals x squared, y equals x cubed, y equals square root of x. But now, we have to talk about these in terms of, in this section, we're going to look at this idea of functions. But before we get into the idea of what a function is, we have to sort of go through some other terms. One of those first terms is defining what a set is. And all a set is a collection of objects. And since this is a math class, the objects we're going to be talking about are numbers and other ideas that involve math. And the notation, maybe I should use the notation that's used for sets. And you saw me do it in class when we were sort of wrote our solution set. That's the idea. When I said solution set, it was you're using set notation, and set notation uses these braces. Just because that's how we're going to be writing everything. So there's set notation. When we're doing inequalities, we did interval notation, and there's also set notation. And that's all a set is. It's just a collection of objects. But the objects in this class we're looking at are numbers. But before we get into a function, we also need to define what a relation means. And a relation is a set of ordered pairs. And before, when we talked about ordered pairs, remember ordered pairs are just that x comma y. Those coordinates, those points that we can graph on the x and y plane. So for example, a relation look like this. It's just a set, so we have to use set notation. And it's just a collection of ordered pairs. So 2 comma 1. We can have 3 comma 2. We can say 1 comma 3. We can say, you can have negatives, -1 comma 2. And that we can just close it off. That's what a relation is. It's just a set of ordered pairs. Again, another one, so you can see, it's just, we start our set notation, 3 comma 1, 4 comma -1, 3 comma 2, and then 2 comma 3. Oops, that looks funny, but there. That's what a relation is. It's just a collection, a set of ordered pairs. Doesn't matter, you can have 4 ordered pairs, 5 ordered pairs, 10 ordered pairs. It's just a set of ordered pairs. But inside these relations, we can break them down even further and talk about them in terms of domain and range. Let me block this off here. We can talk about domain. And what domain is just the set. Again, that's the reason I wanted to define a set, because we keep using that word. Is a set of all, it's really important, all x coordinates. So what does this mean? I can show you. For example, let's say if this was set A, and we'll talk about this as set B. I'll use a different color. Let this be set B. Just giving them names so we can reference them. So if I'm going to do the domain of, let's say, A is the set of all x coordinates. So remember, it's still a set, so that means we have to use set notation. And then what that means is you have to look at all the x coordinates of A and then list them out. It has a 2, it has 3, there's a 1, and there's a -1. As you can see, I don't write these in ordered pairs because I'm just looking at that one number, that x coordinate. And that would be the domain of A. It's just a set of all the x coordinates in that A. Now, if we're looking at B, same thing. I have to write the set of all the x coordinates of B. Here, 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 and there. So first we have a 3. We have a 4. Then we have, if you notice, we have another 3. You don't have to, you never repeat in a set, you never repeat the same object. So by object, in this case, for a relation, you're not going to repeat an ordered pair. For a domain, you're not going to repeat an x coordinate. So if there's already a 3x coordinate in your set, I'm not going to write 3 again. I'm just going to write 2. Because this 3 is being taken care of by that one. And then I have 4, and then I have my 2. And that's the domain of my relation of B. And since we're looking at all the x coordinates, there's probably a term for the y coordinates. And that term is called, let me close this off, is known as the range. Just like how the domain is a set of all x coordinates, the range is the set of all y coordinates. So, same thing. If I'm going to list them out, so for example, hopefully this isn't too cluttered up, but for example, for A, that's going to be 1, 2, 3, and just like the last one here, there's a repeat of 2's. I don't have to repeat it. I just have to include it once, and that's fine. And there, 1, 2, 3. That's the domain of A. And here would be, that's the range of A. Now let's see the range of B. That's going to be 1, -1, 2, and 3. So those are all the y coordinates in that relation. And the reason why it's important to know all these terms first, so understanding a set is just a collection of objects. The objects here are x coordinates, the objects here are y coordinates, the objects here are ordered pairs. So depending how you're using the set, you always use braces as your set notation. And then we have a couple more terms. The reason why we need to know all these terms is because when we start defining what a function is, we need to understand domain, we need to understand range, we need to understand relation set, x coordinate, y coordinates, because we're going to be comparing them together. So let's do that now. Let me define what a function is. So, alright, so I paused the video and wrote down the definition just so we can read it together, go through it together instead of me writing it all out and point out certain things. So given a relation, so again, that's why we need to know what a relation means, in x and y. So you see, a relation is ordered pairs, it has x and y. we say that y is a function of x. Again, I highlighted that because that's the idea. We're going to be talking about functions. So y is a function of x. And that's going to be important when we get into function notation. If for each value of x in the domain, so again, the domain is the x, the set of all x coordinates. That's why it says the value of x in the domain. So all these are values of x's. There is exactly, and then highlight this, but there is exactly one. So let me highlight that. That's very important. One. There's exactly one value of y in the range. Again, the range is a set of all y coordinates. That's why it's talking about the y values in the range. What this is saying is that if we're looking at an x in the domain, we have to compare it with the y, and every x in here. So again, it only says each value of x. So it's every single x in your domain can only correspond to exactly one y. It can't correspond to two of them. Again, this only works one way, because sometimes we're going to see where there's a y that can, there's an x that can only correspond to one. What you sometimes see is that you have one y correspond to two different x's, which is perfectly fine in terms of being a function. What we're looking at here is that x can only correspond to one y. So let's see, for example, let's look at the relation a, since we have it right here next to us. Let's look at a, or I should have said, is a function. That's our question. Is a, the set a function? So that means we have to look at, we're going to look at these right here. So all the values of x and all the values of y, and they have to correspond to only one exact, one exact y. So we have to see, we know we have to look back at the ordered pair, because the ordered pair is telling us what that value of x in the domain corresponds to which one of these y's. So we see that 2, so that's the first one, corresponds to 1y. That's 1y. So that's good. We see that this 3 corresponds to a 2. That's good. That 1 corresponds to a 3. Cool. And -1 corresponds to a 2. You might be asking yourself, but wait, these two are corresponding to the exact same y, and you're right. 3 corresponds to 2, and -1 also corresponds to 2. But the definition says that every x can correspond to only one value of y. That doesn't mean that once that x corresponds to what that y, there is no other x that can correspond to that exact same y. The idea is they're both, even though they're both going to the same one, they're still only going to one y. That's the main idea. That they can literally only go to one y, and that's it. You can have all of them go to that same y, but as long as all the x's are only going to one, then that's perfectly fine. So looking at that, this only goes to one y, this only goes to one y, this only goes to one y, this only goes to the same but one y, that same one y, meaning that a is a function. Yes. Now let's look at if is b a function. So now that means we have to look at all my x's and see that x corresponds to 1y. This 4 corresponds to 1y. This 3 corresponds to a 2. And this 2 corresponds to a 3. Sit there and pause the video and see if you think this is a function or not. Remember, the idea is that the value of x can only go to one y. And hopefully you notice that these two ordered pairs here are using the exact same x. Remember, I didn't have to repeat that 3. In this one, I didn't have to repeat this 3 twice because I only want to show it once, because there is no other 3 on. If you try to, again, these ordered pairs are in different places, but there is only one value of x that's 3 in your entire domain. You don't have multiple x values of 3. There's only one of them. And this one is going to a 1, and this one is going to a 2. So that's why this would not be a function, because this one x is going to 2 different y's. Again, these 2 different x's were going to the same y was okay, because they're still only going to 1. Where this x, again, even though it shows up in 2 different places, it's only one value of x going to 2 different y's, meaning that this is not a function. And if that's not making sense, here's another way that we can sort of identify if these are functions or not. And that's, we can use these things called, mappings. So here's going to be A. Hopefully this makes some sense to you guys. So this is going to be A. So we have all our, let me not do that yet. This will represent our x, our domain. This will represent our y, so it's our range. I'm going to put D down here for domain, R down here for range. Let me move it up a bit so you can see. And we know, remember, the domain of A, we have it up here. It was 2, 3, 1, and -1. And for y, we had 1, 2, and 3. So again, I'm just using these. 2, 3, 1, -1, 1, 2, 3. But we have to see. Remember, this 2 corresponded to 1. This 3 corresponded to 2. This 1 corresponded to 3. But then this -1 corresponded to 2. So here you can see how these two are going to exactly one y value. Even though 2 going to the same one, that's perfectly fine. It's in the wording. It's going to the same 1. So it's only going to one of them. That's why this is okay. You can have all of these go to 1, and that would be perfectly fine. Whereas for B, let's draw that one. So for B, let's draw our domain and range here using a mapping. So our domain is our range. Our domain was 3, 4, and 2. Again, I'm just looking here. And our range was 1, -1, 2, and 3. Now I have to look back at my relation. 3 goes to 1. 4 goes to -1. But then this same 3, so this exact same 3 here, it looks like there's 2 different ordered pairs. But here I only wrote 3 once. You can see how there's only one 3. But this 3 is going to that 2. And 2 goes to this 3. Again, 2 going to 3, it's only going to 1. 4 is only going to -1, so it's only going to 1. But then this 3 goes to 1, 2 different y values. These 2 different x's are only going to one y. So that's perfectly okay. Whereas this is not okay. So this was a function. This is not a function. Again, because it can only go to exactly one value of y. Again, what I was saying, let's say if we had another mapping, this would be perfectly fine. Let's say we had a mapping. I'm going to make this up. This is another relation I'm making up. I'm going to call this relation C. Let's just say this is 1, 2, 3, 4. And we have -2 here. All of these, this could be one relation. What that means, like if I actually rewrote it as an ordered pair, this relation would be 1 goes to -2. And then I have 2 goes to -2. And then I have 3 goes to -2. And then I have 4 goes to -2. So this is working backwards. So this would still be a function. Oops. That's still perfectly fine. Just to exaggerate that idea of all the x's can go to 1y, but that's still a function because they're only going to 1y. There's only one y value in that domain, and they're all going to that 1y. As soon as the x went to another one, let's say this x here had gone to some other y, then it's not a function. Because of that part only, that will make it not a function. So this idea, we want to now extend it to those equations that we were looking at last time. So we saw x squared, x cubed, absolute value of x, square root of x. There's even the cube root of x that we didn't graph, but we can graph later. Yeah, actually, let me give you a quiz right now, and that would be perfect right here. So quiz. The quiz is to graph, this equation, y equals cube root of x. So that's a quiz. You do it and email it to me as a PDF if you can. So make sure you do that. So, but for now, we saw these as equations. And they're made up of, if we look back, I have it right here. We have, all of these were different ordered pairs. So this one was -3 and 3. This was -2 and 2. This was -1 and 1. This was 0, 0, smiley face. This was 1, 1. And then this was 2, 2. These are all ordered pairs. And they are made up of this equation. So technically this equation is creating a humongous relation. Because here's a point here, here's another ordered pair, here's another ordered pair, here's another one, here's another one, here's another one, another. There's an infinite amount of ordered pairs on this graph. So the idea is we want to be able to see if these equations define functions. But they get tricky because here, all we did was look at the relation. But we saw, I just said here's just a few of them. But we just saw that there's an infinite amount of ordered pairs on this graph. So I'm not going to be able to verify every single ordered pair to make sure that it's going to exactly only one y and then call it a function. So then what we have to do is see how can we determine if something functions another way. So the way we did it first was just use the definition, and I looked at it, yes, no, and then we saw the mapping, and we saw how this mapping worked. But another way that we can determine if these are functions or not is we can just graph these ordered pairs. Remember, we learned how to put these on a graph. So let's do that. Let's graph them. So let's do A first. So use the same color. This is going to be A. And let's actually graph A and see how it's going to look. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, because these are ordered pairs. I know I can put an ordered pair on this XY plane. So let's see. This is how the definition tells you how you can find if a relation is a function or not. This is like a visual representation on how if you see this, that's okay. If you see this, that's not okay. Now we just want to see another visual representation of these ordered pairs on a graph. So I'm going to graph them. Hopefully you have them, but I'm just going to look at the paper on my side. So the first ordered pair was 2, 1. So I move 2 to the right, up 2. So that's my first ordered pair. My next one is 3, 2. So I'm going to move 3 to the right and up 2. My next ordered pair was 1 and 3. So I move 1 to the right and up 3. My next ordered pair is -1 and 2. So I move 1 to the left and then up 2. So this is how it visually will look like a... So I'm going to scroll this down so I can have this up here. This is visually how it looks on a graph if I actually put all these ordered pairs on here. Now, we know that these two looked kind of funny, right? It almost seemed, and what these two are, that was 3, 2, that's this one here. And that's this one over here. That was this -1 and 2, 3 and 2. So again, that we might have thought like, wait, those two are going to 1. So it almost seems like it's failing the definition of what a function is. But those two are going to the same one, meaning that that's perfectly okay. There's nothing wrong with that. But now let's graph B, because that one was not a function, and we know the ordered pairs that made it not a function were these two. So let's see how that looks on a graph. So I'll move this out of the way so I can move this up and you guys can see me graph it. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oops, that one came out kind of funny. But here, let me graph these. So for the first one, we have 3, 1. So I'm going to move 3 to the right, up 1. There's a 1 there. I have 4, -2. So sorry, 4, -1. So 1, 2, 3, 4, and then down 1. I have 3, 2. So I'm going to move 3 to the left and up 2. And then I have 2, 3. So 1, 2 to the right and then up 1, 2, 3. Here. So if we're looking here, so let me go back to this one. Now here there was 3, 1 is this one. 4, -1 is here. 3, 2 is here, and 2, 3 is here. But we know this one was not a function. And it wasn't because of the 4 it wasn't this ordered pair. That was perfectly fine. 4 to -1 was perfectly fine. The issue was these two. So let's see where these two are on this XY plane. And then maybe the orientation of them will give us an idea of why it is not a function. And these are it right here. These were the two ordered pairs that made this relation not a function. These were the two ordered pairs that almost made it look like it wasn't a function, but we know that it was. So let me graph C now. Just, I mean, hopefully you're sitting and thinking about this. Think about the orientation of them. And maybe I'll give you an idea of why these are functions or not functions. But let me grab C. You guys can see me graph it. I'm trying to fit it right here because it doesn't move too much. So I'm going to go here. 1, 2, 3, 4, 5. 1, 2, 1, 2, 1, 2, 3, 4, 5. And remember, these here, 1 corresponded to -2, so that was this one. I go 1 to the right, down 2. And then, again, this idea mimics how these 2 went to that 1, but now I have 4 going to only 1, and that's still a function. Now I have 2 going to -2. I have 3 going to -2. I have 4 going to -2. And what do you start noticing? These 3, again, this was a function. Check. Not a function. This is a function. Now you have to start thinking of, well, what's the orientation? Again, all of these, if you notice, hopefully you saw this already, these are all on this horizontal line. These are also on the on that same horizontal line, because they're mimicking the sort of the same idea. This idea of multiple values going to only one y. Multiple values only going to one y. But these, if we look at the orientation, they are right on top of each other. So they're on this vertical line. So that's what gives birth. So straight from the definition. So remember, we're going straight. We use this definition to compare the ordered pairs, to look at the mapping, and then put it on this x and y plane. And we have a visual representation of why a relation is not a function, or it is a function. And again, they don't have to be side by side. That's going to introduce, we're going to look at the idea of this vertical line later. The main idea to take from this is that if ordered pairs are stacked on top of each other, that is not going to be a function. Again, there's no other line. There was no other line here that there's no other ordered pair next to it. So that doesn't, the idea of being next to each other right now does not matter. It will matter later. But it was just sort of seeing how that looks on the graph. But all these ordered pairs were perfectly fine. It's not just this didn't make it a function. So I don't want to confuse you there. This doesn't make it a function. The fact that all of these go to only one y, all of these go to only one y, that's what makes it a function. Not that, oh, you see some that are side by side. Because you might see an example. Let me graph a small one here. You might see one like this, here, here, and maybe here. So none of these are on that horizontal line, and none of these are on that vertical line. Again, we don't care about the horizontal part. We care about, are there any stacked up against each other? And if we notice, there's nothing here, there's nothing stacked up there, nothing stacked up here. Hence, that is going to be a function because none of them are stacked on top of each other. I'll worry about them being side by side later, but right now the main thing I'm worried about is that I don't want them to be vertically above each other, because if they are, that means it is not a function. And this idea of being above each other, maybe, I'm sure you guys are already thinking it, is it gives birth to this idea of the vertical line test. Because if you saw me, I was already doing it. Look, I was making these vertical lines and I was showing you how there is no other ordered pair on this vertical line but this one. There was no other ordered pair on this line but this one. There was no ordered pair on this line but this one. There was no other ordered pair on this vertical line but this one. Hence, that's what made it a function. So now I can just use this vertical line test to help me see if any relation or any graph, any equation is a function or not. So here, let me write the definition out. All right, I wrote out the definition. I paused the video. I wanted to write it out all first so we can discuss it. Maybe, again, I wouldn't copy this first. I would just listen to me going through it. You can always copy it later. So again, it says consider a relation. It's going based off the definition of a function. It's going starting off the same way because this vertical line test is testing if a relation is a function. And that's what is literally going off this definition, given a relation. So consider a relation defined by a set of points x, y. Again, given a relation in x and y. Consider a relation defined by the set of points x and y. This means the same thing. These are other words that are starting that same definition of what it means to be a function. But this is using the vertical line test to verify if your graph, your relation, your equation is a function. So graphed on a rectangular coordinate system. So this definition was looking at the relation as these ordered pairs, domain and range. But now this vertical line test again is looking at, this is the coordinate system. They call them the x and y plane. They call it the Cartesian plane, the real plane. This is that rectangular coordinate system. So rectangular because everything is done sort of in like boxy. We go left, up, down, like it's all boxy. It's not like we're not going from the origin and then curving. We're either going left, right, up, or down. So that's sort of in rectangular. If we think about a box, it's going in these sort of boxy shapes. So that's rectangular coordinate system. The graph defines y as a function of x. We say that y is a function of x. Y as a function of x. Again, it's the same definition. This is just worded for the vertical line test. So the graph defines a function of x if no vertical line intersects the graph more than one in more than one point. That was exactly the same as this. That for every value of x in the domain, there's exactly one value of y in the range that corresponds to it. So for every x, there's exactly only one corresponding y. It could be that one corresponding y goes to multiple x's, or just to one of them, but the idea is it can only go to one y. And that's what the vertical line test is saying. Because if we make a vertical line here, it intersects at this point, and it intersects at this second point. So there, it intersected already more than once. As soon as it intersects more than once, then it's definitely not going to be a function. So we can use this. Like I said, we're looking at the ordered pairs. Here we're only looking at 4 ordered pairs. If I'm looking at this equation here, like I said, how many ordered pairs are on this graph? There's an infinite amount. That means I'll literally have to check here, and then make sure that none of these ever correspond to more than 1. So what I could do, well, I know this graph points in that direction forever, in this direction forever. And then I can see, well, wait. Am I ever, any vertical line that I make, here, 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 here. So again, the idea, as soon as it intersects your graph more than once, your equation, your relation, whatever you want to call it, as soon as you intersect more than once, that means it's not a function. Again, you can do this forever because you know this goes this way forever. And then now you have to just make an interpretation. Do you think that as long as this goes on forever, do you think that this vertical line will ever cross this equation or this graph more than once? And I wish I could hear your answers. Hopefully, I'm getting a bunch of no's. That this vertical line can never intersect this graph more than just that one time. I'm not mean add up all these intersections. Just for that one line, there's only one intersection. For this one line, there's only that one intersection. For this one line, there's only this intersection. For this line, there's only this intersection. So that means at all these, anywhere on this graph, it's only going to intersect it once. Meaning that this is actually a, this is a function. That's pretty valid. Here, I have some other ones that we looked at. This was at the square root. So again, I know it stops here, and then it continues that way forever. And if I look at the ordered pairs, these numbers, because look, I plugged in 0, 1, 2, 4, because these are, again, 2 worked, but then getting this number is weird, so it's just easier to use nice numbers. Again, another square root that we know would be the square root of 16, square root of 25, 49. And if you notice, what's happening is this constantly keeps going up. Again, it doesn't shoot up, but it just gradually keeps going up every single time. So that means every vertical line that I make, I have to ask myself, are any of these vertical lines going to ever intersect this graph more than once? And hopefully you're saying no, because that means that this is going to be a function. That works perfectly fine. Here, let's look at all the ones that we looked at. This was the y cubed. So be careful here, because again, even though this looks like it's going straight up, it has more of an angle. It's still going to the right a little bit. So that means every time I make a vertical line, I have to ask myself again, even though here it might look like it's intersecting, but it's still only intersecting at this one place. Since that, if I keep doing it again, this keeps going to exaggerate it. This goes like that forever. So every time you make a vertical line, anywhere on this graph, it's going to look like this. Anywhere you go here, it's always going to keep going like that. Same thing down here, but down here it's going to look like this. Curving, vertical, 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 vertical. And it's never going to cross the graph more than once. Hence, this is a function as well. Here, then we also looked at this x squared. Same thing. These open up forever. So when I'm making my vertical lines, am I going to intersect this graph more than once? Nope. Hence, this is a function. Now, eventually, we're going to talk about, there's this, I'm sure you're already thinking of it, about, there's also a horizontal line test. And here, it would actually intersect twice. But I don't want to get into that right now. The main one right now is the vertical line test, meaning that as long as it doesn't intersect your graph more than once, it is a function. So here are the ones that we graphed. So remember them. So again, this passes vertical line test. This passes vertical line test. This passes vertical line test. So does this. And so does this one. Here we know a line goes like this forever. So we'll always be able to verify it. So all of these are considered, not only are they equations, but they are also functions. But hopefully you're asking yourself, does that mean everything is a function? And of course not. Not every single equation is a function. For example, let me give you some examples here on this sheet of paper. Let's do it on the corner though, just to sort of block this off here. So for example, let's say we're looking at a circle. If I was looking at a circle, then this is where you want to make more than one vertical line. You don't want to just be doing one vertical line to verify if something is a function or not. Because if I make a line right on the edge of that circle, it might seem, well, look, I only intersected it once. Oops. I only intersected it once, hence is a function. Same thing. If I do it right on the left edge, it might seem, oh, look, I only intersected once. But I'm not trying to make the graph pass. I'm trying to see where I can make the graph fail. And here, that's where this fails, because here I cross the circle, and again 2.2 is about circles, and I'm going to bring it back when we look at chapter 7. But looking at these two, now we cross the graph more than once. We intersected it more than once. Hence, this will not be a function. Not a function. And there's also other graphs that we've looked at that are other equations that aren't. So if you guys remember, the one that we did look at a lot was a vertical line. That's whenever x is equal to some constant, it makes a vertical line. This is a linear equation. So before you start thinking all linear equations are functions, well, the vertical line is also a linear equation. But if I make, again, I don't want to be making a vertical line over here. I'm not even touching the graph here. So this doesn't matter. I want to do it right where I touch the graph. And how many times am I intersecting this graph? Here's 1, 2, 3, 4, 5, 6. I'm actually going to intersect this one an infinite amount of times. The definition says as soon as it intersects more than once, it's not a function. This one intersects as an infinite amount of times. Hence, this is like super not a function. Again, there's no such thing as super not a function, but this is just me exaggerating how it definitely has no chance of being a function because it intersects it so many different times. So that's part of what this section is about, being able to identify which one of these are functions. And then we're going to talk about notation, because we're going to take all these y's and we're going to replace them using something called function notation. This is really important. We're going to make y equal to this, we call it f of x, because that means y is a function of x. That's what those definitions kept saying. Y is a function of x. So that means here I'm going to write f of x is equal to mx plus b. Here I'm going to write f of x is equal to x squared. and so on and so forth for all of these. So then we're going to get into what can we do with these functions now. So I'm going to pause the video here, and we're going to see what else we can do with these later.